All right, everybody. Well, welcome to CC Colloquium for November 10th, 2021. I'm thrilled to welcome you here to, as some of you may have kept track of and recall, we are trying every semester to feature one of our esteemed established faculty. And we're going to hear from one of our special faculty today. Before that, a couple of announcements, or at least one. Earth and Space Exploration Day is this weekend, this Saturday. It's a virtual program. I don't know if maybe, Kim, maybe you could put the link in the chat for people who are tuning in online. What time does that start, Rick? From 10 a.m. to 1 p.m. It's a virtual program, ESE Day. Hopefully the last fully virtual ESE Day forever. But yeah, we're counting on that. All right. And also one other announcement. Next week, we have, one of the other things we've started doing the last couple of years is to have every semester a set of student presentations. So next week, we're going to hear from 4 of our graduate students, Santosh Harish, Lena Hefferin, Lucia Perez, and Joe Zaleski. So please come, at least half of them. I think 3 of them are going to be in person. So it'd be great to come in person and be able to give them a real audience. And so with that, I'm happy to turn this over to Maitri Bose, to Professor Bose, to introduce our speaker.
Thanks, Dario. Good afternoon, everyone. I'm absolutely delighted and honored, actually, to be asked to introduce our speaker today. So he is Dr. Sumner Starrfield, who is a professor in our School of Earth and Space Exploration. So Sumner finished his PhD from University of California, Berkeley, and he worked briefly at Yale University and IBM. I didn't know that. And finally joined ACU faculty in 1972. And he's been here since. In 2002, he was honored as the Regents Professor, a title that's reserved for faculty of exceptional ability and who have achieved national and international distinction. He's a computational astrophysicist. So as one, he primarily makes stars explode on his computer using code. He also observes real-time explosions with a whole suite of telescopes operating at different wavelengths. During his PhD work on the Nova outburst in DQ Hercules, he figured out the mechanism for Nova outbursts. So why do these stars explode? And that theory still prevails. Okay, I don't know whether he'll get into that, but so look up his papers. He's the fellow of the Royal Astronomical Society, fellow of American Physical Society, as well as the founding fellow of the American Astronomical Society. He's had a long list of students and postdoc mentees who are very well employed. He's received innumerable invitations to present at in plenary talks and colloquiums. And he also has an asteroid named after him, which is so cool. So he collaborates with scientists all over the world. Several of them are present here today, virtually. And my collaboration with him started with my job talk back in 2017. And it has already resulted in so many published papers. So he publishes a lot and works really quickly and swiftly. The thing I love about him, as I worked with him, I've come to know him quite a bit. And the one thing that I really love about him is his dry sense of humor. No pressure, Sumner. So with this brief introduction, I wanted to say that today he's going to talk about how novae make lithium and why we need to understand the evolution of low mass, low metallicity stars in globular clusters. So Sumner, did you want to go ahead and take away?
Okay, thank you. Are we recording? Yes, we are. Okay, thanks, Kim. Okay, so you saw my title, you read it. Here are my collaborators who have taken part in much of the work that I'm going to be telling you about. Theory, Rafe Hicks, who's Theory Division Director at Oak Ridge National Lab. Christian Iliadis, nuclear physicist, who just stepped down as chair at UNC. And of course, you all know Maitri. And this was up before I knew she was going to introduce me. And then Chick Woodward and Mark Wagner. So here's the outline of my talk. Big Bang nucleosynthesis. I'll be saying BBN most of the time and not the whole thing. And where lithium comes from in the early universe, it turns out, as typical in astronomy, there's a problem. And I'm thought myself of a possible solution. And I've talked to my collaborators, especially my Italian collaborators, and they sort of agree and disagree. So I'll tell you something about that. But I certainly want to emphasize that whatever I say is controversial and requires more work. And I'll give a homework problem. And then we can use meteorites to determine the galactic lithium-7 abundance. I'm going to be talking just about lithium-7 because it's produced one way. Lithium-6 is produced a different way, and I'm not only briefly mention it. Okay, and the person who's done this work is someone that I think everybody in the audience, or most people in the audience, know, and that's Kathy Lauders at WashU in St. Louis. We also make lithium in classical novae. I'll tell you how we do that and the observations. I'll show you some of the observations because those are pretty recent. Tell you what a classical nova is, and show you how classical nova makes lithium. And just to tie everything together, especially since meteorites are an important part of CC, we do know that there's stuff from classical novae in the solar system. So I'm showing a figure from the book I use when I teach beginning astronomy, just because why not use a professional artist instead of my cartoons? So we start with the Big Bang, say from 3 to 10 minutes. You can all read everything. And you know, here are protons there. And after about a few minutes of evolution, the protons get together with the neutrons. You can tell protons are red, neutrons are gray, at least to the textbook, and make helium-4. Okay, so that's 24% in the first 3 or 4 minutes are made then. Why is that so fast? Well, is this in the way? Do I need to get rid of this? Can you see the right part of the screen? I can't tell.
Yes.
Okay, so this is not in the way.
I can read the whole slide if that's what you mean.
Okay, let me get rid of that. And now you can read the, anyway, this is my own computer. What can I say? All right, so Big Bang nucleosynthesis theory suggested that the early universe consisted of protons, neutrons, and electrons. And I showed you the cartoon. Well, these are both from the beginning book. And here's the really neat thing about BBN. At temperatures of about 10 to the 9th degrees, and remember the temperatures are falling rapidly as the universe expands, okay, the neutrons get together with the protons, right? No charge on a neutron, and make deuterium. And the deuterium immediately makes helium-3. The helium-3 combines with other helium-3 to make helium-4 and get rid of 2 protons. This happens very fast. And so in a very short period of time, about 24% of the elements or the protons and neutrons become helium-4. Okay, and this is based on estimates of the early universe expansion rate. Why are the neutrons so important? This is the first step here on the right of the proton-proton chain that causes the energy production in our own sun. Okay, now we've got 2 positive charges. One of those positive charges, one of those protons has to decide to become a neutron, right? There it is down there. That means it's a weak interaction. So we get rid of a neutrino and we get rid of a positive electron just to balance everything on both sides of the equation. Well, in the sun, the center is at about 15 million degrees. The density is about 150 grams per cubic centimeter. The reaction from one proton to the other has a mean lifetime of billions of years. So we need something to make everything go faster. Okay, well, What happens to the helium-3 and the helium-4? They can make beryllium-7. Okay, now there are two plots here. One is from the WMAP results on the left. The other is from another book that I use for beginning astronomy. And there are some points that I want to make on this. First of all, this actually was first done by Dave Schramm. And the one you're looking at comes from a plot from Gary Steigman in the Encyclopedia of Astronomy and Astrophysics. You can examine the conditions at the beginning of the universe, at the Big Bang. Excuse me, where'd that come from? You know what? Mail. I quit mail. There we go.
Yeah.
Okay.
This looks great now.
Okay. Anyway, Gary Steigman. I'll show a picture of him, actually. Now, here's the WMAP observation. They obtained the density of ordinary matter relative to photons very, very accurately. Call that precision cosmology now. So not just based on measuring the abundance of helium and deuterium and helium-3 and lithium and trying to decide what this value is. But you can see that as the conditions, as the density increased from right to left, the helium increased, more collisions, even if the temperature is dropping. The deuterium goes away because that's being eaten away very fast. Helium-3 goes away slightly. Lithium goes through some contortions before reaching this value right here. Again, do the abundances agree with what they need to be? And the cosmologists say no. The other point here I want to just make on the right, because they actually say it's the same underlying x-axis. The WMAP, the abundances all tell us there's not enough material in the universe to close it. That is, it's not going to reach a given size and then collapse back down. Okay, it's open, the universe will expand forever, and I'm not going to talk about dark matter or dark energy today. Okay, so how much lithium, if I take that value that it should be and ask how much of that actually gets into our galaxy, the prediction is about 250 solar masses. I'm going to use two different ways of expressing this and try and keep those straight for you. Now, here's the problem, the cosmological lithium problem. When we go to the most metal-poor stars, we find there's only about 80 solar masses. Okay, so about a third. This actually causes the cosmologists contortions. Okay, they emphasize studies of the cosmic microwave background are precision enough, so that's probably not the answer. Nuclear physics, they look at all of the reaction rates, that's probably not the answer either, but they're baffled. And so a baffled physicist claims, well, maybe we need new physics. This is sort of, different from a baffled astronomer who throws in magnetic fields. The third way is maybe there's something happened to the measurements of the lithium and the metal poor stars. And that's what I'm going to talk about briefly. Okay, so back in 2006, A.J. Korn et al., this is in Nature, okay, why not look at the influence of diffusion? I hope you can read that. I sort of highlighted it. Diffusion theory on the evolution of stars. And they chose a globular cluster, NGC 6397, to investigate. Now, in the middle are the definitions of the things I've put on the plot right here on the left. We want to look at iron on top, lithium on the bottom. Okay, so TO, let me go to this and then come back. here, it's an astronomy talk. You need to actually see an astronomy picture that's gorgeous. That is a picture of NGC 6397. Now, as part of looking at this picture, I found this paper in 2009, 3 years later, where they investigated, they took spectra of stars along the main sequence, okay, and compared green to red, found there were differences lower in green, slightly higher in red, and decided it was on the evolution. Let's go back here. Here's what these people did. They took 4 different points along that Hertzsprung-Russell diagram, okay, turn off of the main sequence, subgiant branch, base of the red giant branch, and the red giant branch, okay? And they, instead of that color index on the bottom, they actually did it with effective temperatures. And you can see that iron is low. This, by the way, is a logarithmic plot, okay, 5.4, etc., is low compared to the population that we think of for 6397. It slowly grows, though, and reaches the value that they like. What's going on? You take a star, let's call it 8.8 solar masses. It has a convective zone at the surface. As it evolves off the main sequence, that convective zone goes deeper and deeper. Now, these stars are like 11 billion years old. There's enough time for the heavy elements to settle out. People call it diffusion, gravitational settling, diffuse out and actually lower the abundance with time. And that's what's probably what they think happened. The other people don't quite agree, but that's okay. Now, as the star evolves off the main sequence, the convective zone goes deeper and deeper and starts bringing some of the iron that settled out back up to the surface until finally a large part of the star is convective and the iron is back normal. Okay, now let's look at lithium. First of all, you have to realize that lithium is a very fragile nucleus, lithium-7. It fuses at about 2 million degrees, which is not that far from the surface in many of these stars. So here it is, this star, and these are collections of stars, okay, have reached an abundance. I'll come back to that once I've gone through the explanation, okay, and the lithium abundance has dropped. This particular value here, about 2.3, is called the Spite plateau. It's named after 2 French astronomers whose name is spelled S-P-I-T-E and is pronounced Spite. Okay, and you can see that the lithium has settled out. But now as the convective zone starts moving inward, it reaches a point where not only is there no lithium because it's been fused, but now it brings the surface lithium to depths where it's fused away and essentially it disappears. What are these units on the left? You can see temperatures on the bottom. The Big Bang prediction is a value of 2.7. You can see that's right here. The old stars that we're measuring is 2.3. That's there. The present galaxy in these units is 3.3. And it's a logarithmic plot. The lithium people generally call this A, but that's just no reason to do that. And I believe that this unit was actually devised by Phil Mouskoff's brother-in-law. Okay, so here we are. They talk about evolution, they talk about diffusion and gravitational setting, but you know, they waffle around and raise their hands. Here's the problem. One of the places where lithium, the Big Bang lithium, could be depleted is in pre-main sequence evolution, where the star is completely convective for a while. It would seem interesting to take a modern stellar evolution code like Tycho or MESA, take 0.8 solar or 0.7 solar mass stars, pre-main sequence, follow their evolution. Both codes include diffusion, I know that, and rotation, maybe some overshooting of convection, and see what you find. That's a neat little problem that we could solve here at ASU. We have the tools. Okay, moving on. Where's the 3.3? I said that's present galaxy. This comes from Kathy Lauder's, okay, 210 to the minus 9. All right, that's what we get in meteorites. We convert it to that A value, get 3.3. If we convert it to solar masses, and that's what you do, first we have, it's number density, convert to mass fraction, how much mass in the galaxy, pick your favorite number. This is baryonic mass, and we get about 1,000 solar masses. Here's the point. This is where it's destroyed. Where does the new lithium come from? And that's the part of the next part of the talk. Well, all of the papers now cite the Cameron and Fowler mechanism. The mechanism's on the left. I'll explain it in a second. I just want to show you, this is Willie, that's Willie Fowler. That's Al Cameron. I'm trying to talk too fast, okay. This was the day that it was announced in 1983 that Willie had been awarded the Nobel Prize. It was the first day of a meeting on nuclear astrophysics, okay? And so it was sort of took over the meeting. This is Gary Steigman on the left. He is well known for all of his contributions to cosmology and particle physics. Unfortunately, he passed away in 2017 after a fall. This person on the right is Dave Arnett, U of A now. He's a student of Al's, and Patrick Young is a student of Dave's. So Patrick is a grand student of Al Cameron. So here's the mechanism. You've all been reading it while I've been talking, but you make beryllium-7 at the bottom of a deep convective envelope, helium-3, helium-4. We need to move it to the surface on a very short time because the lifetime of helium-3 against, excuse me, the lifetime of helium-3 against captures of the alpha particle at these temperatures is only a few hours. Mix it to the surface, excuse me, leave it on the surface and let it decay to lithium with a 53-day half-life. And frankly, this is a short summary of a classical nova outburst, which I predicted back in 1978, okay, and followed up by new calculations by Jordi Jose and Margarita Hernandez in 1998. Where does this picture come from? There's the entire group at the meeting just for fun. I won't even mention, some of you probably recognize some of the other people there. I'm just gonna say I'm not responsible for the gender distribution. Okay, so this is a picture that Margarita, a friend of ours, put in to Nature when the Japanese astronomer using high dispersion spectroscopy at the Subaru telescope discovered beryllium-7 in this particular nova back in 2013. You can see what's going on. Here, the proton-proton chain is occurring. Hydrogen and deuterium make helium-3. Helium-3 and helium-3 make helium-4 and 2 protons. But helium-3 can capture helium-4, go to beryllium-7. If the beryllium-7 gets out to where there's no nuclear reactions going on, like this one, it will decay over 53-day half-life to lithium-7, captures an electron, by the way, K capture. and emits a gamma ray at 478 kilovolts. So that's what's going on. So here are the observations. These are the beginning sets of observations by Tajitsu, and I'll show you some others. Actually, I won't. But this is beryllium-7 here. It's at about 3130 angstroms. These are angstrom units, okay? These are the God-given units, not nanometers or funny stuff, okay? And this is a nova, V5668 Sagittarius, V2940 Oph, constellation, variable number. Here's beryllium-7 here. There's an isotopic shift, so we know it's not beryllium-9, which is the stable beryllium isotope. And it's singly ionized beryllium. And then the observers compare it to calcium and so on, and calcium and so on. So this was 69 days after the discovery. We know beryllium-7 is radioactive. It had to be produced in the outburst, 80 days after the discovery. Okay. Well, Luca Iso discovered lithium in this nova. This is part of his PhD, by the way. So here is 6707, 6707 in V1369 sand. Now, 3 of us have done the same thing using Pepsi at a high resolution, 270,000 on the Large Binocular Telescope, southeastern Arizona. And here's lithium. Okay, they also saw beryllium-7 in this nova. Okay, and what you probably, it's hard to see, is that it's disappearing. In fact, it's reasonably strong on day 13 after the discovery, and it's pretty well gone by day 21. What's going on? The nova ejecta are ionizing. So here's our conclusion, and that's Chick on the left, Chick Woodward, Mark Wagner on the right. He's the instrument scientist at the LBT, and Chick is a faculty member at the University of Minnesota. Second direct detection. Okay, the first was by Luca Iso. They're significant, and as it ionizes, it goes away. The initial lithium is destroyed by the TNR, that a thermonuclear runaway. Okay, I'll define that later on. And we're observing lithium coming from the decay of the beryllium-7. Okay, so how much do we get from classical novae? Well, there's 2 times 10 to the minus 10 is our prediction. I'll show you those predictions later on. There are about 50 novae per year in the galaxy, which is about 10 to the 10th years. And so we predict, just based on our results, about 100 solar masses from classical novae. The point that I'm going to show you is the observations imply about 7 to 10 times more lithium is ejected than we predict from our simulations. So maybe classical novae make most of the lithium in the galaxy. This is a plot from Paolo Malero and Trieste. And you can't, well, you'll see it on the next one. Here is a series of results from novae on this same log number density plus 12, okay? So this is nice and positive. Remember, galaxy from meteorites is 3.3. So these are various different novae. Orange is with, assuming it's decayed from the beginning and not, so of course it's going to be larger. These are different kinds of novae. These are oxygen neon, these are carbon oxygen, and you can see that they're all considerably higher than the galaxy. This gray area is our predictions from a paper we published in 2020. By the way, for those people who like to know things like how small the world is, Paolo was a friend and colleague of Sandra Pizzaretto. Okay, so here is the figure caption, it says pretty much what I've just said. He just sent me this a week ago. And I'm going to go right on. So what is a nova? It's a new star, appears, stays bright before fading back to quiescence. So here's V838 Mon, wasn't a nova, but this picture shows what I'm trying to say. And then the amateurs and professionals start plotting the brightness in some units. It's a logarithmic unit here as a function of time. This was a nova that we studied back in 1993. We actually studied it with the International Ultraviolet Explorer satellite. And it stayed bright for about 40 days and 40 nights before falling precipitously because it formed dust, small grains of material in the expanding gas. And as it cleared, we could see through it. It got so dense, we couldn't see any of the optical light. It was all redistributed to the infrared. And then it slowly decayed over the next few years. And we haven't really looked at it lately. Of course, here's a different light curve. This is a recurrent nova. This is its outburst in 2006. It also went off back in August of 2021. So we've been going crazy. This is X-rays. And I just want to point out, the X-rays are not smooth. These are real data points, and it goes through huge variations in count rate over days and so on. And when we measure where all of the energy is being output in the X-rays, we're getting temperatures for this object of around 700,000 to 1 million degrees. So it's really hot. Novi eject about 10 to the -4 solar masses into space, and material is enriched in these elements. And aluminum-26, we're probably not responsible for all of it, but we're responsible for a good fraction of the aluminum-26 in the galaxy, which is of course important in the solar system. Here are pictures of the expansion of nova material away from 3 different novae. I'm going to concentrate on 1974 SIG. It went off in 1992. And we got it with HST 464, 723. And then we got it again with the LBT, the MODS spectrograph on Halloween 2013. And realized since it was Halloween that we didn't want to display it this way. We had to display it this way and make the obvious connection to that. Okay, back to IUE and spectra. Here are 2 different galaxies, 2 different novae and 2 different galaxies. And you can see that the features look very, very similar. And this is a 3rd nova, went off in 1991. Spectra taken by Bob Williams, no oxygen, but sulfur. Now, as a graduate student, Karen Van Landingham at ASU, she's now an associate professor at Westchester University, Pennsylvania, plotted the various abundances that she measured for 3 different novae. Black is solar, red is HER91. You can see it sort of agrees up here for carbon. It falls below for nitrogen, whereas these 2 other novae are pretty in good agreement. It falls below solar for oxygen and up for sulfur. We're still trying to understand that. What happened? How did we get rid of all the oxygen? So here's a summary of the outburst. Lasts about a year. Peak luminosity exceeds the Eddington luminosity. That's what helps drive the material off. Ejecta speeds from about 300 to 8,000 kilometers per second. The ejecta abundances are far from solar, including lithium and beryllium. Helium is always enriched. And there are 2 composition classes. And as usual in astronomy, there's an outlier. This particular nova did not eject any hydrogen, just helium and carbon. And we think it's what we would call a helium runaway, but it turns out to be interesting. Okay, so let's switch to the theory. And why do we care? Nova outburst is the largest hydrogen bomb in the universe. Think about that. They occur on the white dwarf component of a close binary stellar system. This is actually an artist's conception of the RS Ophiuchi outburst, where the white dwarf explodes inside the outer layers of the red giant. Does that cause high energies? It causes very high energy gamma rays, as a matter of fact. Okay, the white dwarf is actually accreting material from its companion. Okay, so its core is carbon and oxygen, or oxygen and neon. Now, as the white dwarf increases in mass, its radius, its degenerate material, its radius decreases. So one solar mass white dwarf has a size about the radius of the Earth. But the mass is increasing, the radius is decreasing, its surface gravity increases. So we should expect a lot of changes in the outburst depending on the mass of the white dwarf that we're studying. So here's what we've done with our code happens to be called Nova for obvious reasons. And we accrete either onto carbon oxygen or oxygen neon core. 3 different compositions. I'm not going to spend a lot of time on this. 6 white dwarf masses. We can either assume that the mixture occurs right at the beginning. We did that for many, many years because we had no better idea what to do. Now, using 3-dimensional results from Casanova, Jose, Calder, and Shore, we can determine that the mixing occurs during the middle of the thermonuclear runaway. Here's a series of plot from their paper back in 2016 showing time, and they're just doing neon 20, but you can see the core material moving up once the thermonuclear runaway is ongoing. This was all solar. It's a 3D code, so they can't follow it very long, but you can see the flow of gas up into the accreted envelope. And that's what we try and mimic using a 1-dimensional code, which allows us to go much faster and study more things. The important isotopes are what we call the beta decay isotopes: nitrogen 13, O14, O15, fluorine 17, and 18, which all decay very short time scales. But nothing happens once they've been produced. There's no proton captures except for this one. And so the most abundant nuclei in the envelope will become the beta decay nuclei. We call that the last 3 minutes. Convection forms, okay, and reaches the surface. At about temperatures greater than 10 to the 8th, proton captures are fast enough so for these nuclei to become the most abundant in the envelope. Convection mixes them to the surface. Energy generation at the surface exceeds 10 to the 15th, and they provide the energy release to eject the shell, and their decay products are enriched in the ejected gases. So here are 2 plots. I'm not going to have time to show a lot of this. So this is carbon oxygen core mixing during the thermonuclear runaway. Okay, here's, if we assume 25% of the material of the core has been brought up into the surface, here are the temperatures we get at the core accreted matter interface. Here is what happens if we assume 50%. We're bringing a ton of carbon in, fresh carbon. When the temperatures are like 50, 60 million degrees, we get a shock. That shock moves through the envelope and ejects material. This is now for the most massive white dwarf. going down to the least massive white dwarf. And you can see the scale on the right. Here, this is 6,000 seconds. This is 2,000 seconds. It happens very much faster when we increase the carbon abundance. So here is now that same 50% core, just showing the total nuclear luminosity reaches values of 10 to the 14th. In the center of the sun, it's around 100. So this is quite an explosion. And this is oxygen neon, same thing. We take the same starting model, but now instead of putting in carbon and oxygen, we put in the composition of an oxygen neon white dwarf core. And you can see the temperature, there's no carbon or very little. Temperatures only get up to about 350, not 650 million degrees. And everything happens a bit more slowly. I don't even put the 0.6 on. It evolves much too slowly. So the composition affects the evolution, the white dwarf mass affects the evolution, and so on. Here is how much mass is ejected as a function of white dwarf mass. This is just for carbon oxygen. The oxygen neon accrete most of the material. They eject a very small amount, so I didn't even put it on. Okay, and this is mostly accreted material. So this may eject at 1.2 solar masses, white dwarf masses, 80%, but that's still only a fraction of what's been accreted. So here's the summary of that. This is related directly to the supernova 1A problem, that white dwarfs in classical novae are growing in mass, and if they can get to the Chandrasekhar limit, they could possibly explode as a supernova of type 1A. What about the lithium? Here are 4 production plots. So here's lithium is over here. This is really mostly beryllium-7. You can see that this is logarithmic plot ratio to solar. Here's 1. And you can see that lithium is about 1,000 times solar at 1 solar mass, about the same at 1.35, 50-50, here's 25-70. Again, the mass and the core composition really don't have that much effect. It's pretty much about 1,000 times solar in our predictions. So here's the results, both CO and oxygen neon. And you can see that the number that I quoted earlier, about 210 to the minus 10, it's pretty flat here for carbon oxygen, 25-75, and 50-50. And then the oxygen neon come up, but they still reach this value. So the 210 to the minus 10, once you take all this, that's that gray area you saw in Paolo's plot. So here's that 1,000 solar mass again. Here's the 100 solar mass. I've already said this before. Again, the observations, I showed you Paolo's plot, about 7 to 10 times more lithium is ejected than we predict. What's the answer? We don't know yet. We've got to think about what possibly might be going on. Okay, now this is a plot from Maitri and a paper in the APJ in 2019, taking some of these results I've just shown you, comparing them to isotopic abundances for silicon carbide stardust. And the 4 or 5 red squares there are the ones that we predict are actually nova grains, come from Novi. So there's nova ejected material in the solar system. And there's a picture of her lab. All I know about laboratory astronomy is don't cut the red wires. And this is another plot. Fly a U-2 aircraft with flypaper, pick up anomalous interplanetary grains, done by Bob Pepin, those of you who know about neon E know that name. Compare neon nova, these asterisks, to the abundances that he's measured in the laboratory. And you see that the asterisk in red, asterisk in red, asterisk red, all seem to fall pretty close to each other. And the interesting thing is that there was no helium-3 measured. And of course, that's our prediction, that helium-3 is destroyed. So there's grains. So do I have, well, yes. Consequence of accretion onto white dwarfs in close binary systems. Core matter is mixed with accreted material. Temperatures in the explosion sample the regime, where cross-section, this is great for nuclear physicists, because in fact, the temperatures are high enough so you don't have to extrapolate them to low energies. Ejecta abundances depend strongly on nuclear physics. Core composition is either carbon-oxygen or oxygen-neon. Non-solar abundances for all elements. Possible galactic source of lithium and these odd isotopes, and aluminum-26. I'm not going to turn that one down. So white dwarfs and carbon-oxygen classical novae are growing in mass. They may produce all the lithium in the galaxy. And I put this in for people who are going to look at the recording. These are the citations for this talk. And I'll leave you with this about lithium-ion batteries made with recycled materials can outlast newer components. And I'll stop here and ask for questions.
All right, thank you very much. So we have people in the audience more than usual. So if there are questions here, we can start here, and people online, just put them in the Q&A and we will get to them.
Should I stop sharing?
Yeah, sure.
Yeah, let me.
Hey, Sumner, this is Sean Bryan. So I guess the bottom line is you're saying the element abundances are not some kind of crisis in cosmology. Like there's enough, going on in the stars that no one shouldn't be worried if that last digit isn't quite right.
Absolutely. I don't know why. I mean, Brian Fields, who's written reviews, says diffusion, and then goes on and says maybe it's new physics, but they don't, they talk about different kinds of new physics, but they certainly don't really think about the fact that we're looking at stars that are, at least the 6397, they're like 11 or 12 billion years old. And if they don't show the abundances that you want, there's got to be something going on. And there's diffusion, gravitational setting, evolution. There's mixing, convection. As I say, it's a great problem for somebody at ASU.
All right. Question online. So are novas basically a white dwarf burping from overeating their partner star's material?
Yes. What more can I say? Yes. And they're recurrent. The typical classical novae, most of those that I showed you or talked about in Paolo Malero's plot are not recurrent in the sense that we haven't seen them go off more than once. The fact is that they probably occur every 100,000 years, but the nova explosion does not destroy the white dwarf. It's there, and it's going to go through this evolution again.
So that perfectly sets up the next question from Steve Ruff, who asks, I wasn't aware of recurrent novae. How does a nova recur?
If you take a massive white dwarf and you stick it next to a red giant, which is transferring material very rapidly, it can occur on extremely short timescales. We've done those models. I didn't talk about them today. There is a nova in M31, right? The great galaxy in Andromeda that's going off about once a year. and almost like clockwork. And we've been studying it since 2008. It's due to go off again in December. So everybody's tooling up to get it again. As I said, RS Ophiuchi has gone off a number of times. 2006, we had enough time to publish all the results. The middle of August, we've actually gotten the paper out already. We're working on more data. It's been studied by everything. And it includes things I didn't talk about, like very high energy gamma rays.
Other questions, either online or in person? The soon-to-be Professor Nittler, who's here visiting with us, has a question.
Hey, Larry,
Sumner.
sorry I missed you. I didn't know you were here.
I'm happy on the day I happen to be here. I got to hear your excellent talk. Is there any hope of measuring the gamma ray from the 500 keV or 480 or whatever it was from beryllium-7 in these novae?
Yeah, we need a better set of flying detectors. There's the Advanced Compton Telescope, which has an increased detection area and sensitivity over integral. Right now, when we take our calculations of the lithium or beryllium-7 decay, production, and the nova has to be within about half a kiloparsec, 500 parsecs, in order to be able to detect those gamma rays. Now, there's a completely different story, which you probably already know about, is the detection of very high energy gamma rays from novae. And that comes from shocks, internal and external shocks. And that's the Fermi Large Area Telescope. A lot of that, the Naval Research Lab is pretty involved in that.
All right, another question online. Do different galaxies have different frequencies or incidences of novae phenomena?
Yes, they do. And I invited the person who's done most of that work to actually attend the talk. That's Alan Shafter, UC San Diego State. And if he had a chance to listen, he could probably chime in himself. But yes, different galaxies have different nova rates. And there's some controversy. I don't think it's controversial, but some of my colleagues do, the observers do, of the nova rate in our own galaxy. And Alan did a superb job of getting 50 novae per year. And then people look and say, oh, they're going to study the center of our galaxy where everything's hidden through gas and dust. And they find more novae going off there than Alan did, and they get a smaller number. I wasn't the referee, fortunately.
All right. Other questions? Anyone? All right, well, if there aren't any other questions, let's thank Sumner for that presentation. And we'll see
You're
many of you
welcome.
back here next week. Thanks, Sumner.
Okay, you're welcome.
Thanks, Sumner.